order the wrong relay configuration for your earthing system, and honestly, you are in for an absolute nightmare. You're either going to get nuisance trips on perfectly healthy equipment, or, and this is way worse, you'll completely miss a real catastrophic ground fault. Welcome to this explainer. In our previous discussion, we saw exactly what a short circuit does to a transformer, and why speed matters so much. But today, we're going to see how selectivity doesn't just happen magically when you flip a switch. It starts long before the relay is even powered up. It literally starts with a diagnostic table and selecting the exact right configuration for your specific network. Okay, let's dive right into this. Meet the ABB RET615 protection and control relay. Its entire job in life is to continuously watch currents and voltages and command a breaker to trip the very instant something goes wrong. Because, well, transformers are insanely expensive, they take forever to replace, and they fail fast. But here's the catch. To protect a two-winding transformer properly, you absolutely have to match this hardware's internal software configuration to your network's physical earthing. And you do this using a specific diagnostic table. So here is the roadmap we'll follow today to properly diagnose and select your restricted earth fault protection setup. Number 1, the high stakes. Number 2, the invisible fence. Number 3, low versus high impedance. Number 4, the golden CT rule. And finally, number 5, decoding the configurations. Section 1, the high stakes of avoiding commissioning failures. This is all about how to match an RET615 configuration labeled A through H to your exact earthing arrangement. What a lot of folks miss is that engineers frequently treat restricted earth fault, or RF protection, as this generic one-size-fits-all feature. It is absolutely not. Mixing up the specific implementations of RF at the specification stage, that's one of the leading causes of massive commissioning delays. Order the wrong one, and it simply won't commission. Section 2, the invisible fence, also known as the REF protection concept. So, what is this actually doing electrically? In plain English, reef protection draws an invisible fence right around the transformer winding and its neutral connection. Any fault current inside that fence, bam, the relay trips immediately. Anything outside that fence, the relay completely ignores it. You see, standard overcurrent protection just cannot reliably distinguish an internal ground fault from current that's merely flowing through during some external fault. Reef protection exists to give you that true pinpoint selectivity. It's kind of like a magnifying glass zooming in on the one spot most likely to hide a small fault, the neutral point. And that brings us to the first major fork in our decision tree, Section 3, low versus high impedance types, because we're actually dealing with two structurally different technologies that just happen to wear the exact same ref name. Notice the stark contrast here. On the left side, we have low impedance ref, technically called LREF-PNDF. This is a highly flexible, software-driven numerical scheme. Best part? Zero extra hardware. Now on the right, we have high impedance ref, or HRF-PDF. This is the traditional old-school method. It's a hardware-stabilized physical scheme that gives you extreme sensitivity for faults near the neutral point, but it heavily relies on an external, physically high impedance path, like a stabilizing resistor, to keep the whole scheme stable during external faults. To make this super easy to remember, think of low impedance ref like a universal remote. It uses numerical algorithms right inside the relay to compensate for mismatched equipment using software. Super adaptable. High impedance ref, on the other hand, is like a fixed key deadbolt. It absolutely demands that all your hardware matches exactly, and it requires those external resistors. It's way less flexible, but man, once it's set up correctly, it is rock solid and virtually unbeatable. Okay, so how do you choose between the universal remote and the deadbolt? Well, you don't just guess. That brings us to Section 4, the golden CT rule for selecting impedance. Let's walk through the diagnostic logic here. Step 1, always verify your current transformer or CT turns ratios first. If your phase CTs and your neutral earthing CT have different turns ratios, say you've got a 2000/1 phase CT paired with a 1000/1 neutral CT, you are automatically restricted to Step 2, low impedance RFF. That mismatch alone completely forces the low impedance path, no matter what your personal preference is. Now, if and only if the ratios are perfectly identical, you move to Step 3, where you actually have the luxury of choosing between high or low impedance. So, listen to this stern warning. Never, and I mean never, mix a high impedance ref scheme with mismatched CT ratios just to see if it works. During an external fault, all that mismatched current has nowhere to go but straight through the relay's operating coil. Since high impedance doesn't have software compensation, you are guaranteeing a false trip, or worse, you're going to fry some components. In older brownfield retrofits where you might have legacy CTs with mismatched ratios, low impedance ref isn't just a compromise, it's literally the absolute, correct, and often only workable choice. All right, we've got our diagnostic logic down and we understand the golden CT rule. So let's hit section 5, decoding the configurations. We're going to map everything we just learned directly to the RET615 configurations. Check out this selection matrix straight from the manual. The relay gives you 8 standard configurations, A through H. Configurations A and E are for your high-voltage earthed neutrals using low-impedance REF. B and F are for low-voltage earthed systems, again, using low impedance. Now, configurations C and G protect the high-voltage side, but they use high-impedance REF. And finally, D and H protect the low-voltage side using high impedance. The big takeaway here? Choosing C, G, D, or H strictly requires equal CT ratios. Let's look at how this plays out on an actual schematic. On the left, we've got configuration A. On the right, configuration C. Both are designed for transformers with earthed high-voltage neutrals, so they both draw that invisible protection fence right around the HV side. But look really closely at the function blocks. Configuration A on the left uses the low impedance block, which completely handles mismatched CTs purely through internal software. Configuration C on the right uses the high impedance block, requiring identical CTs and usually an external stabilizing resistor, which you can actually see noted right there in the physical circuit path. Now let's move over to the low voltage side and see how this builds out. We're contrasting configuration B on the left with configuration D on the right. Both are for solidly earthed LV side transformers. Just like before, configuration B uses that flexible, software-driven low impedance block. Configuration D uses the high impedance block. Remember, if you order configuration D, you are locking yourself into that matched CT requirement. If your site has mismatched CTs, you absolutely must order configuration B or F instead. Okay, let's do a quick interactive check to test what we've covered today. Imagine you're out in the field working on a real-world brownfield retrofit. You check the physical equipment. Your phase CTs are rated 1000/1. Your neutral CT is also rated 1000/1. And your neutral is solidly earthed on the LV side. Apply the decision tree. Which REF type are you actually allowed to use, and which configuration letters apply? Take a second and think about it. Got your answer? Let's reveal it. Because the ratios match perfectly, you actually have a choice here. High impedance ref is safely on the table, which means you could use configuration D or H to protect that LV side. Honestly, this is often the traditional, ultra-stable choice that a lot of engineers specify by default when they've got matched hardware. However, low impedance ref, configurations B or F, is also fully compatible. It doesn't strictly require matched ratios, but it definitely accepts them, making it a perfectly valid and flexible choice too. Let's wrap this up with the core rules of thumb you need to take away from this explainer. First and foremost, you absolutely must read the network's earthing diagram and verify the CT turns ratios before you specify your relay configuration. Second, differing ratios instantly eliminate the high impedance options, so you can just say goodbye to config C, D, G, and H. And finally, whether your transformer is earthed on the high voltage or low voltage side is going to dictate the final configuration letter you select. The CT ratios dictate the tech, and the earthing dictates the letter. So by matching the relay's configuration to your network's actual earthing and CT setup, you have ensured your invisible fence is drawn perfectly. You are not going to suffer those frustrating commissioning failures. But that does leave us with one final, pretty provocative thought. Once your digital relay is perfectly configured with all the right software, how do the physical instrument transformers, the actual devices feeding all this current data into the relay, handle the massive, chaotic violence of a real physical short circuit? We're going to explore exactly how hardware survives that extreme stress in our next explainer. Thanks so much for joining me, and keep learning.